Today we study graph algorithms. First, I will review graph basics and graph representation. So I think you've learned graph basics in discrete mathematics and data structures, but today I will review those topics. A graph G is a pair V and E. V is a vertex set and E is an edge set. A vertex is a standalone object, and it is usually represented by circles. And an edge is an object connecting two vertices, and it is either represented by an arrow or a line. So if it is a directed graph, edges are represented by arrows. And if it is undirected, edges are lines. And there are other names. Vertex is sometimes called a node, and an edge is called a link. A directed graph is a graph with directed edges. Edges have directions, so they are represented by arrows. And an edge leaving a vertex U and entering a vertex V is said it is incident from vertex U and incident to another vertex V. And this blue edge is incident from vertex 2 and to vertex 4. And in a digraph, that is a directed graph, there are self-loops. Self-loops are edges from a vertex to itself. In this case, the red edge is a self-loop. Okay, those are mathematical definition of a graph. And to store them in the computer memory, each vertex is identified by a number or a name. Usually they are identified by numbers. So 6 circles have their numbers, 1, 2, 3, 4, 5, 6. And then each edge is identified by the ordered pair of vertices. Look at this. In this case, there are 1, 2, 3, 4, 5, 6, 7, 8. 8 edges. And this blue edge is represented by a pair 2, 4. And this edge is represented by 4, 5. And this edge is by 5, 4. And in a digraph, there are at most 2 edges between vertices. And an undirected graph is a graph with undirected edges. Edges have no directions, so they are represented by lines. And there are no self-loops. So edge u comma v is the same as edge v comma u. So 2 comma 4 is the same as 4 comma 2. So because there is no direction for an edge, this blue edge is called being incident on vertices 2 and 4. We don't say it is from one to other. We just say it's on 2 and 4. And adjacency. If vertex, if an edge u, v is an edge, vertex v is adjacent to vertex u. So don't be confused. Don't be confused. I'm not saying u is adjacent to v. I'm just saying that v is adjacent to u. Okay? If the graph is undirected, then this relation is symmetry. If u is adjacent to v and v is adjacent to u. In a directed graph, it is not symmetry. Look at this graph. Because look at this edge, then vertex 2 is adjacent to vertex 1. But vertex 1 is not adjacent to vertex 2 because there is no edge from vertex 2 to vertex 1. And then degree. The out degree of a vertex is the number of edges leaving it. Okay, look at this vertex first. What is the degree of vertex 1? Park Jong-hun. What is the degree of vertex 1? Out degree of vertex 1. 1. Why? Yes, it has only one outgoing edge. So the out degree of 1 is 1. 박근배.
네.
What is the in degree of vertex 1?
1.
Yes. Why?
It's from 4.
Yes, it has only this incoming edge. So its in degree is 1. 김범진. 장영민.
예.
What is the in degree, out degree of vertex 2? 3. Why?
4, 2 to 4, 2 to 5, 2 to 2.
Yes, there are 3 outgoing edges, 2 and a self loop. 배민희, 신지수, 박준규. And then what is the in degree of vertex 2? Speak up. 2. Yes, there are 2 incoming edges, so its in degree is 2. And then when we say a degree, it is the sum of the out degree and in degree. So the degree of vertex 2 is 5 because the out degree is 3 and its in degree is 2. If the graph is undirected, then the out degree and the in degree cannot be defined. Only the degree of a vertex is defined. In this case, the degree of vertex 2 is 3. Okay, then I will explain a path. A path from a vertex U to another vertex V is a sequence of vertices. V0, V1, V2 through Vk. And V1 should be U and Vk should be V, because it's a path from U to V. And every vertex Vi plus 1 is adjacent to Vi. That is the same as there is an edge Vi, comma Vi plus 1 for all I. Look at this example. 1, 2, 4, 5 is a path from 1 to 5. Why? 최소리. 김종빈. Why is it a path? Yes, there is an edge from 1 to 2 and 2 to 4 and 4 to 5. So it is a path. And how about this? 1, 2, 4, 1, 2. 신경식. 신경식? 어미송. Why is this a path? Yes. 1, 2, 4, 1, 2. So, because there is an edge between every adjacent vertices, so it is a path. And vertices can be repeated. 1 appeared twice and 2 appears twice. No problem. And how about this? 1, 2, 4, 2. 손광훈. Is it a path? Yes. 1, 2, 4. It's fine up to now, but there is no edge from 4 to 2, so it is not a path. And then the length of a path is the number of edges in the path. For example, the length of a path 1, 2, 4, 5 is 3 because it has 3 edges in the path. And if there is a path from vertex U to vertex V, and V is called reachable from U. So vertex 5 is reachable from vertex 1. Why is it reachable? 권다운. 김현준. Why is it reachable? Yes, what is it? Yes. When you are asked to prove that U is reachable from V, your answer should be like this. You have to show there is a path from V to U. In this case, this path verifies that vertex 5 is reachable from vertex 1. But vertex 3 is not reachable from vertex 1 because there is a cut here. So there is no path from 1 to 3. And simple path. A path is simple if all vertices in the path are distinct. Look at this. Look at this path. 1, 2, 4, 5. All vertices are different, so it is a simple path. But look at this path. 1, 2, 4, 1, 2. Vertex 1 and 2 appears twice, so it isn't a simple path. Okay? And cycles and simple cycles. A path is a cycle if V0 is the same as Vk. And a simple cycle is if these are distinct from V1 to Vk. Look at this. V0 can be the same as Vk. Look at this. Look at this path. 1, 2, 4, 5, 4, 1. Because the starting vertex is the same as the ending vertex, it is a cycle. But it is not simple. Why? 4 appears twice in the cycle, so it isn't a simple cycle. But this cycle, 1, 2, 4, 1, is simple. So only if the first and last vertices are the same, it is a simple cycle. And then I will explain 3 definitions. First, on a cyclic graph. It's a graph without any cycles. Then it is called a cyclic. And a connected graph. And it is defined on undirected graphs. An undirected graph is connected if every pair of vertices is connected by a path. Okay? So when you are asked to show that a graph is connected, then you have to show that there is a path between every pair of vertices. And then finally, connected components. It's maximally connected subsets of vertices of an undirected graph. So guess how many connected components are there? 문경식. How many connected components are there? 박영호. 이동우. 5. Why?
1, 2, 5랑 3이랑 6이랑 서로 연결했으니까 4는 연결이 안 돼 있잖아요. 나머지 5개만 연결되는 거 물어보시는 거 아니에요?
Okay, the answer is 3. There are 3 connected components. So this is a connected component because these 2 vertices are connected, so they are in the same connected component. And these 3 vertices are in the same connected component. And 4 is in a standalone connected component. Okay? And this is important. Maximally. That is, if we have only these conditions, that is, every vertices should be connected. Then, as you said, this one can be a connected component, only 3. But this component is included in this component, so it isn't maximal. So we only choose maximal subsets. So there are only 3 connected components. Okay, then let's move on to directed graphs. On directed graphs, we say a graph is strongly connected if every pair of vertices is reachable from each other. So we can also define strongly connected components. They are maximally strongly connected subsets of vertices in a directed graph. Count the number of strongly connected components in this graph. 1, 2, 3, 4? 1, 2, 4, 5. Yes, this is a strongly connected component. Why? Okay, how can you show that? Look at this cycle. Look at this simple cycle. Then, because all vertices are on this cycle, there is every vertex is reachable from any other. So this is a strongly connected component. So, but, okay, you said there is only 1, but the answer is 3. There are 3 strongly connected components. Okay, you're right. This is not a strongly connected component, so we can separate them. So this vertex only is a strongly connected component, and this vertex is also a strongly connected component. Okay. And let's consider a directed version of an undirected graph. This is a directed graph, undirected graph. And if we replace each undirected edge by 2 distinct bidirectional edges, then it is a directed version of its original graph. Okay? And symmetrically, we can consider an undirected version of a directed graph. In this case, replace each directed edge by an undirected edge. So these 4 edges are converted to undirected edges. But look at this. These 2 bidirectional edges are converted to only 1 undirectional edge. Okay. And then let's consider this question. There is an undirected graph G, and consider its directed version G prime and undirected version of G prime, which is G double prime. Then are G and G double prime the same? And also consider this problem. Yes, they are the same. try some examples. Then you can find they are the same. How about the second one? 강인구. Why are they different?
처음에 방향성이 있다가 방향성이 없어졌다가 생길 때 어떤 방향으로 생긴 점이랑 다를 수 있어요?
But we make both. We make both directions. 박성현.
맨 처음에 한쪽에서 한쪽 방향으로만 있던 게 양쪽 방향으로 생길 수 있어요.
Yes. Look at this. First we have a directed graph, and this is its undirected version. And then consider a directed version of this graph. Then between vertices 1 and 4, there are two bidirectional edges, but the original graph has only one edge, so they aren't the same. And a complete graph. A complete graph is an undirected graph in which every pair of vertices is adjacent. Look at this. This is a complete graph with two vertices. And this is a complete graph with three vertices. And this is a complete graph with four vertices. Okay, then a short question is, what is the number of edges with n vertices? Think it over. And choose two. Yes, so we have this number of edges. Why? Can you explain?
Because every two vertices has edge. So
Yes, it's the same as the number of selecting a pair of vertices. So that's, and choose two. And then a bipartite graph. And it's an undirected graph. And in the graph, the vertex set can be partitioned into two subsets, V1, A, V2, such that for each edge UV, they should be in different partitions. So edges should cross this partition. There is no edge in the same partition. That is the definition of bipartite graph. Okay, and how about this? Is this graph bipartite? Ichiho. Is this bipartite? Yes, it's a bipartite graph. Don't be misled by this circle. If we partition them in a different way, we can show that they are bipartite. Can. Okay. Reading comprehension. Can is different from the other. So can be partitioned. Okay, then I will explain forest and tree. forest is an acyclic undirected graph. 조정환, is this a forest? Yes. Look at this. There is no cycle and it is undirected. It's a forest. How about this? Is it a forest? Yes. Undirected and acyclic. How about this? No. Why not? Yes. There is a cycle. So it isn't a cyclic, so it's not forest. And 3. 3 is a connected forest. So a new condition is added. Connected, acyclic, and undirected. Then let's check them one by one. 최경렬. Is this a tree? Yes, it is connected, acyclic, and undirected. How about this? Is this a tree? Why not? Yes, it's not connected. So this is not a tree. How about this? Is this a tree? Why not? Yes, because of this cycle, it isn't a tree. Okay, then a DAG. A DAG is a directed acyclic. Oh, something is missing. Oh, it's here. A DAG is a directed acyclic graph. So it is a directed graph without cycles. Look at this. It's not a DAG because it has a cycle. Right? No, this is not a cycle. Look at this carefully. So there is no cycle in this directed graph, so this example is a DAG. Don't be confused. Because of the directions, we cannot make a cycle. And handshaking lemma. If a graph is undirected, then the sum of degrees of all vertices is the same as twice the number of edges. Try to understand why it is true. Yes, in this case, because it is undirected, there is no in or out degrees. Okay, on edge contributes 2 degrees. Okay, so if there is an edge, the degree of 2 vertices are increased by 1. So if we add all the degrees of vertices, it is the same as twice the number of edges. Okay? And then let's try to understand the 3 characteristics more. The definition of a tree is connected, acyclic, and undirected graph. But a tree satisfies these 4 characteristics. The first one is any 2 vertices are connected by a unique simple path. And if any edge is removed, the resulting graph is disconnected. And if any edge is added, the resulting graph contains a cycle. Finally, the number of edges is 1 less than the number of vertices. Okay. I'll give you a couple of minutes and try to understand why it is true. Assume that it isn't unique. Then we have two different paths between these two vertices. Then we can create a cycle including these two vertices. So the path should be simple and unique because the tree is acyclic. Okay, so this is a very important property. Any two vertices are connected by a unique, simple path. And then the next one, if any edge is removed, the resulting graph is disconnected. Yes. So look at this edge. It's a unique, simple path between these two vertices. Okay, so if we remove this edge, the unique, simple path between these two vertices is disconnected. So this is true. And the last one, 현운율. 윤영주. Okay, if any edge is added, the resulting graph contains a cycle. Why? Okay, so look at this. So there is a already connected path here. So assume that we are adding a new edge between these two vertices. And then by this property, they are already connected by a unique simple path. And this path plus this edge constitutes a cycle. So if we add a new edge here, then this is a cycle. So it's true. And the last one is can be proven by induction. So just remember this. The number of edges is 1 less than the number of vertices. And I said this is the definition of a tree, and these 4 things are tree characteristics. But the tree definition, there are a lot of tree definitions. This is the one we used, connected, acyclic, undirected graph. But this definition is the same as if in a graph, any two vertices are connected by a unique simple path. So this characteristic can be used a definition. That is, from this definition, we can show that this is true. Or the graph is connected, and if any edge is removed, the resulting graph is disconnected. This can be used as a definition of a tree. Or connected and this. Or acyclic and this. Or it is acyclic and this. So any of these things can be used as a definition of a tree. So we will use one of these definitions, anyone convenient. And let's consider the number of edges. Okay, look at this undirected version first. And we counted the number of edges in a complete graph. So there are these number of edges where n is the number of vertices. So in an undirected graph, this inequality is true. Look at this. Why the maximum number of edges in a directed graph? Great. So this is the maximum number of undirected edges, and they are multiplied by 2 and sub-loops. So it is n squared, 3 squared. Or it can be a choosing with repetitions. So from now on, I will explain graph representations. There are two famous representations: adjacency list representation and adjacency matrix representation. This is the adjacency list representation. Look at this. There are 6 vertices. So we create 6 lists. And each list is an adjacency list of the vertex. Okay, look at this. From vertex 1, there are 2 outgoing edges. They are to vertex 2 and vertex 4. So this list includes vertex 2 and 4. And then, how about this? This vertex 5 has 1 outgoing edge, and it is to vertex 4. So it has only vertex 4. So we consider only outgoing edges. Okay? If the graph is undirected, we store both directions. Look at this. Sorry. Okay. So we store 2 in an adjacency list of 1 because it stores this edge in this direction. And consider the reverse direction, an edge from 2 to 1. Then we store 1 in the adjacency list of 2. So the directed version of this graph is stored in an adjacency list. Okay, then the storage is this. Theta of V plus E. Why? This is an array, and this array has elements which is the same as the number of vertices, and V elements, and then count the number of nodes in these linked lists in total. Then it is the number of edges multiplied by 2 in this case. Or if it is this, then it is just V plus E. In this case, V plus E and the number of edges is multiplied by 2. But asymptotically, they are the same, V plus E. Okay, then let's think of another representation, adjacency matrix representation. In this case, we initialize a V by V matrix. So because there are 6 vertices, we create a 6 by 6 matrix. And each entry is 1 or 0. And it's 1 if there is an edge. Look at this. There is an edge from 1 to 4. So this entry is 1. From 1 to 4. But there is no edge from 4 to 1. So this entry is 0. So in this way, we can store 1 or 0 in the matrix. So what is the space consumption? Simple. It's V squared. Theta of V squared. And this is an undirected version. As I said, this edge means both directions, from 1 to 5 and 5 to 1. So we store 1s on both entries, 1, 5 and 5, 1. Okay, then can you see the symmetry along the main diagonal? So ij, the entry, the value stored in entry ij is the same as the value stored in entry ji. So we don't have to store the whole matrix. We store only the half. So upper diagonal or the lower diagonal. Triangle. We store only one of them. Like this. So because it is undirected, the values in the main diagonal are zeros. So we store only these values. Okay, I'll explain from this page next week. So, any questions?